Welcome back. In this video, you'll learn about several ways to prepare text for processing. Text data usually needs some cleanup before you can start processing. Typical cleanup tasks can be performed by tools such as AWS Glue Data Brew or Amazon SageMaker Data Wrangler, or through Python code. No matter what method is most appropriate, you perform some general processing tasks. For example, you'd remove leading and trailing whitespace and change the case to lowercase or uppercase. You'd remove HTML, XML, or other markup tags. You'd also convert numerical values to text. For example, imagine that you'll need to process some prices as text data. You'd change the numerals in a price of $9.99 to their word equivalents. Continuing with the typical processing task, you'd also remove punctuation. And finally, you'd reformat the text. As with all tasks, you'll need to experiment to see what gives you the best results. Tokenization splits text into smaller parts using whitespace and punctuation. The sentence, "I don't like eggs," could be tokenized into these tokens: the letter I, the word fragment don't, the letter T, the word like the word eggs, and the period. Exactly how this is done depends on the tokenizer you use. The generated tokens are then used in the next steps of the processing pipeline. Stop words are words that both frequently appear in sentences and that don't contribute too much to the overall meaning. Removing stop words will reduce the number of words that need to be converted to numbers for the machine learning algorithm to learn. In the example, the meaning of the sentence isn't lost by removing the stop words. Be careful not to remove stop words that are appropriate for the business problem you're trying to solve. For example, when performing sentiment analysis, you'd want to keep words such as not, because they can change the sentiment of the sentence. You can make your own list of stop words. Many ML packages provide lists of stop words that have been curated. One example of this is the Natural Language Toolkit, or NLTK. It's often easier to start with those pre-made lists and exclude specific words that you want to keep. Like most other ML tasks, you'll need to experiment with the stop word removal to see what strategy gives you the best results. In the English language, a word has many different forms that can be used grammatically. For example, consider this word series based on the stem play. You can have play, plays, playing, and played. When you build a model, you'll want to make sure words with the same meaning have the same impact on the algorithm. A simple way of solving this is to remove the trailing suffixes, such as the suffixes used to indicate plurals or verb tense like s, es, ing, and ed. There are two main stemmers in use, the porter, and snowball. Porter implements a set of rules to perform on the word. Snowball modifies these rules and can give slightly better results. Stemming works for many words, but not with irregular verbs such as taught and teach, and brought and bring. Stemming doesn't consider if a word is a noun or a verb. For example, the word saw could either refer to the see or saw, depending on if the token is a verb or a noun. To solve these issues, you'll need to use another technique called lemmatization. Lemmatization is another technique used in NLP. It works by considering the morphological analysis of the words. With lemmatization, you can map the words taught, teaching, and teaches to the word teach. NLP tools provide functions to perform lemmatization, which are derived from language-specific dictionaries that are produced by human beings. These dictionaries map a word back to its lemma, and they account for the context of the word. It's easier to build a stemmer for a language than it is to build a lemmatizer. Stemming tends to be faster because it performs some string manipulation. A lemmatizer is slower because it needs to look up each word, and you might also need to calculate what part of speech a word is. Which tool gives you the best results depends on the type of problem you're solving and the trade-offs you can make in performance versus accuracy. In the example, the lemmatized version has fewer tokens because are and was are mapped to be. This could improve the results of the model you're training depending on the problem. You can use managed services to perform many text processing tasks. Both AWS Glue Data Brew and Amazon SageMaker Data Wrangler can perform many of these cleanup tasks you've learned about in this section. The tool you use will depend on your data processing requirements. Now, one advantage of Data Wrangler is that you can use custom scripts. These scripts can be Python code snippets that manipulate the data. In this section, you learned about some of the common text preprocessing tasks. Text cleanup includes converting the case to a standard case, removing white space, removing HTML tags, and converting numbers to text. Tokenization covered converting sentences to words and punctuation. Stop word removal looked at removing commonly used words from sentences to reduce the number of features. Stemming covered using simple parsing techniques to return a word to its root form, while lemmatization looked at using human-curated lists to map words back to a common form. These are some of the tasks you might do when you prepare your text. Not all NLP tasks need all of these steps, and you should experiment with each problem to see which task gives you the best results. Thanks for watching. In the next video, you'll get an overview of how to create numeric representations of words with vectorization. Hi, and welcome to Section 4, Text Vectorization. In this section, you'll learn how to convert text data into numerical representation. Bag of words is also known as BOW, and it converts text data into numbers. BOW does this by first creating a vocabulary from all the words in all the documents. Then it calculates how the word occurs in the text. Occurrences can be counted in 3 ways. The first way is binary, which indicates if the word is present or not present. The second way is through word counts, which count how many times the word appears in the text. And finally, the third way is through frequencies, which is a count of the words that are normalized across the document. One challenge for BOW is how to handle the new words that weren't part of the original vocabulary. This problem is known as out of vocabulary, or OOV. You'll come back to OOV later in this section. We'll now walk through an example over the next few slides. This example uses these 3 sentences. It is a dog. My cat is old. It is not a dog. It is a wolf. With a simple binary bag of words, there's a 1 in the column if the sentence contains the word. Otherwise, the column has a 0. Note that there's no context, order, or meaning in the output. It doesn't consider the popularity or rareness of a term. Binary just indicates if the word is in the text. A word count bag of words indicates if a word was present, and it also counts the number of times that word appears. This method is slightly better than binary, but there's still no context, order, or meaning in the output. Word count also doesn't consider the rareness of a term. A term frequency, or TF, increases the weight for common words in a document. The formula in the example is relatively simple. For the text, it is a dog. The terms are a, dog, is, and it. Because there are 4 words in the document, each word gets a score of 0.25. The text, it is not a dog, it is a wolf, has a total of 9 words. The term wolf appears once. Applying the formula, we get 1 divided by 9, which equals 0.11. Applying the formula to the word is, which occurs twice, results in 2 divided by 9, which equals 0.22. Now you might be wondering if it's useful to increase the weight of what appears to be stop words. Well, that depends on the problem, but keep in mind that the results would be different if you remove the stop words. Inverse document frequency is also known as IDF, and it increases the weights for rare words in the entire vocabulary, not just in the line of text. The formula is shown here, along with the calculations for each term. As you can see, the terms that appear less frequently have a higher IDF score. The TF-IDF model multiplies the TF and IDF metrics together. TF-IDF is often used for document search and keyword extraction. This example shows how to apply TDF-IDF to these sentences. If you apply the formula here to the term wolf, you get the following results. First, the value of TF is 1 divided by 9, which equals 0.11. Next, the value of IDF is the log of 3 divided by 2 plus 1, which equals 1.18. Therefore, in this example, TF multiplied by IDF would be 0.11 multiplied by 1.18, which equals 0.13. TF-IDF highlights terms that are more unique within a document. For example, consider the term dog. It appears in two documents. It has a TF-IDF of 0.25 in the first document and a TF-IDF of 0.11 in the third document. Why do we get these results? Well, the answer is that the first document has fewer words, so the term dog represents more of the document. In contrast, the third document has more words, so the term dog represents less of the document. Now, compare the situation to the term cat, which has a score of 0.3. Cat only appears in one document, and it's 25% of this document. The term wolf also only appears in one document, but has a score of 0.13. There's a difference in score here because wolf is one of 9 terms in the document, so it's less important than the term cat. Why is this important? Well, if you were searching for the term dog, the first document has a higher score for dog, so the first document is probably more relevant than the third document. Equally, though the term wolf appears in the third document, there's less of a chance that the third document is about wolf because it has many more terms in it. If you asked what the second document was, you could say cat, my, or old. These small documents are a really small corpus, but it's hard to demonstrate. You can imagine many documents using the terms my and old. For example, my old dog and my old wolf. Now, if this were the case, the scores for dog and wolf would drop, but the score for cat would remain high. An n-gram is a sequence of tokens from the text. 1 gram are single words. 2 grams, which has also known as bigrams, contain 2 words. You can also have 3 grams, 4 grams, and n-grams. You can calculate the term frequency of an n-gram like you'd calculate the term frequency of a word. You can use n-grams to determine the next word in a sequence. Now, this is useful for detecting words that can be chunked together. For example, you could combine the words Pacific and ocean together as Pacific Ocean and analyze it as a single term. You can also use this process for checking how words are spelled. For example, say that you have the text Pacific Ocean, which misspells ocean by omitting the E. It could be corrected to Pacific Ocean if there was a high probability that the word ocean occurs after the word Pacific. Thanks for watching. In the next video, you'll learn more about text vectorization. Welcome back. In this video, you'll learn more about converting text to numerical representations. One problem with BOW models is that they don't have information about the meaning or context of the word that's captured. This situation means that relationships, such as contextual closeness, are not captured. This relationship could be as simple as saying that the terms cat, dog, and wolf refer to animals that are often discussed in the context of pets. Well, this is a problem because people do not have pet wolves. Word vectors represent words as multidimensional continuous floating point numbers. Semantically, similar words get mapped to the points that are near other points in the vector. So words such as cat, dog, and wolf should be close together, but the word light bulb should be distanced from these 3 animal words. Word2vec takes an input corpus of words and produces a vector space of several hundred dimensions. Each unique word is assigned a corresponding vector based on the context where they appear in the corpus. These vectors can then be used in downstream NLP tasks. Word2vec is itself an ML model that uses a neural network, which needs to be trained. You can also use a pre-trained model. One such model is Glove, which has models trained from large amounts of data from Twitter and Wikipedia. You can find these models as part of the Gensum GitHub repository. Visualizing high-dimensional data is difficult because the most we can understand visually is space in 3 dimensions or 3D. You can use tools to help visualize data such as T-distributed stochastic neighbor embedding or T-SNE. T-SNE converts similarities between data points to find a representation of those points in a lower dimensional space. You can then plot these points, which could help you understand the relationships visually. Principal component analysis is also known as PCA. It's another method for reducing the number of dimensions. Both the TSNEE and PCA models reduce the number of dimensions. The key difference between them is that PCA creates a linear map of the variables that are in a higher dimension space to a position in a lower dimension space. It only uses the variables that have the greatest impact on the outcome of the model. The T-SNE model creates a similar mapping. However, instead of a linear mapping, it calculates the similarity of words in both the high dimensions and the low dimensions, and it then minimizes the difference between the two sets of variables. When using a trained model, any words that were not part of the original corpus will return a zero matrix. The vectors generated are typically used for downstream NLP tasks such as sentiment analysis, named entity recognition, and machine translation, to name a few. Word2Vec has two variants: continuous bag of words, or CBOW, and skipgram. CBOW tries to predict the target or centered word from the surrounding words. In this example, it would predict the word loves from the context words, which are the, man, his, and son. Skipgram is the inverse of CBOW. It predicts the surrounding context words from the target word. It would predict the, man, his, and son from the target word loves. Both variants return similar results. So it's worth experimenting with which method works best for the business problem you're trying to solve. The Amazon SageMaker Blazing Text algorithm provides highly optimized implementations of the Word2Vec and text classification algorithms. As mentioned earlier, the Word2Vec algorithm is useful for many downstream NLP tasks, such as sentiment analysis, named entity recognition, machine translation, and others. With the Blazing Text algorithm, you can scale to large datasets easily. Similar to Word2Vec, Blazing Text provides the skipgram and CBOW training architectures. Blazing Text implementation of the supervised text classification algorithm extends the fast text classifier to use GPU acceleration with the custom CUDA kernels. You can train a model on more than 1 billion words in a couple of minutes using a multi-core CPU or GPU, and you can achieve performance on par with the state-of-the-art deep learning text classification algorithms. The SageMaker Blazing Text algorithms provide the following features. First, it provides accelerated training on the fast text classifier on multi-core CPUs or a GPU. It also provides accelerated training of Word2Vec on GPUs using highly optimized CUDA kernels. And finally, it provides enriched word vectors with subword information by learning vector representations for character n-grams. Using this approach, Blazing Text generates meaningful vectors for OOV words by representing their vectors as the sum of the character n-gram or subword vectors. For Word2Vec training, the model artifacts include the vectors text file, which contains words to vectors mapping. The model artifacts also include a vectors binary file used by Blazing Text for hosting, inference, or both. The vectors text file stores the vectors in a format that's compatible with other tools like Gensum and Spacy. AWS Glue Data Brew doesn't include transformations for text vectorization. However, Data Wrangler implements Account Vectorizer with TF. It can generate up to 100 new columns, or it can generate a matrix. In this section, you learned about 7 different models for converting text into a model you can use with machine learning. First, you learned about the BOW model. BOW is a simple way of treating each word in the text as a unique entity in the back, which is the collection of all the words. The next model was TF. TF calculates the frequency of a word in the overall collection by dividing the number of instances for that word by the total number of words in the collection. IDF is a more complex approach to frequency. It increases the weight for rare words in the collection of words, and it decreases the weight of common words. TF-IDF is a further refinement of IDF that combines TF and IDF. Next, you learned about engrams, which is a model for breaking the text into tokens of various lengths. For example, a unigram model creates tokens for individual words, while a bigram creates tokens for two-word pairs. Word vectors are a model that assigns a floating point number to each word in a multidimensional model. The advantage of word vectors is they capture context for how the words are used in the document. CBOW and skipgram are two similar models that predict words that surround a particular word in a document. CBOW predicts the central word. In contrast, skipgrams predict the surrounding words based on the word that's in the center of a group of words. And finally, you learned about Amazon's SageMaker Blazing Text, which is an optimized implementation of Word2Vec and other algorithms. Thanks for watching. In the next video, you'll get an overview of some more advanced text processing tasks. Welcome back. In this video, you'll learn more about advanced techniques for processing text. Syntax and semantics are two techniques used in understanding language. Syntax is the grammatical structure, while semantics is the meaning. A sentence could be grammatically correct, but makes no sense. For example, the sentence, "Dogs love to run," makes sense. But the sentence, "Dogs ride bananas," doesn't make sense. Now, both are grammatically correct, but only the first sentence is semantically correct. Here are some important considerations when building applications such as chatbots, personal assistants, or search engines. First, consider word order and meaning. Syntactical analysis looks at how words depend on their surrounding words. Changing the word order might make it difficult to understand the sentence. For example, the sentence, "Alexa, in the Who won Ping Pong 2018, has the same words as the example, but makes no sense. Next, consider whether you should keep stop words. Removing stop words might be good for reducing the dimensions, but doing this can alter the meaning of the sentence. Make sure that you understand the morphology of words. Both stemming and lemmatization will change the words and modify the grammar of the sentence. Finally, identify the parts of speech in a sentence. It's important to identify the correct parts of speech for understanding the correct meaning of a word. For example, consider these two sentences. "Both my dog loves his stick and you need to stick to a schedule" contain the same word stick. In the first example, stick is a noun, but in the second example, it's a verb. All these considerations are important when working out meaning. For example, say that you ask Alexa, "Who won the ping pong in 2018? Alexa needs to understand the structure of the question to answer it. The phrase ping pong relates to an event, and the phrase in 2018 refers to a time frame. The event and the time frame have a relationship to each other. You can find these dependencies by parsing the text. Parts of speech tagging, or POS tagging, means labeling words with the appropriate parts of speech. Parts of speech include verbs, nouns, adjectives, adverbs, pronouns, prepositions, conjunctions, interjections, numericals, or determiners. POS tagging is usually done with the help of a pre-trained tagger. Most taggers use the list of tags from the popular pin tree break tag set. To correctly identify the correct tag, the previous and next words are considered. Understanding the structure of the sentence is a key step when you want to extract information from text, such as names, events, and locations. All other techniques use part-of-speech tags to parse a sentence. To understand common grammatical patterns, you need to divide the words into groups called constituents. This is done based on the role of the word in a sentence. English has three main constituencies that are used in NLP. Now, the first constituency is the noun phrase, which is a phrase built around a single noun. Some examples of this are, "A packet of chips was included with lunch," or "That music video is an international phenomenon." The second constituency is the verb phrase, which is a verbal part of a clause. Here's an example. "She had been living in Hong Kong." The third and final constituency is the prepositional phrase, which is a phrase where the preposition always comes at the beginning. An example is, "I long to live near the live near the beach. After you tag the parts of speech and the noun, verb, and preposition phrases are detected, you can understand the meaning of the words. Typically, for English, the word order is subject, verb, object, or SVO. The basic idea is that a sentence is about something and it usually involves a subject, a verb, and an object. Most sentences are more complex, but the same parsing rules can be applied. In the previous example, who is the subject? In this case, Alexa deduces that the who must be a table tennis or ping pong team based on the object, the ping pong. Won is the verb. The ping pong in 2018 is the object. With this information, you can begin to answer the question. The goal of core-reference resolution is to identify text mentions that refer to the same underlying object. Core-reference can be anaphoric, which refers to the previous text, or it could be cataphoric, which refers to future text. Understanding what the words he, she, or it refers to is important in understanding text and information systems, chatbots, and virtual assistants like Amazon Alexa. In this last section, you learned about some of the more advanced NLP processing tasks, which include POS tagging, so you can understand the individual components of a sentence, constituency parsing, so you can identify phrases from words, dependency parsing, so you can understand the relationship between the words and phrases, and core-reference resolution, so you can identify entity mentions within the text. In later modules, you'll explore some of these topics in more detail. You'll also explore how they're used when you learn about information retrieval and topic modeling. Although specific techniques for these topics aren't covered in this course, they're also useful for building chatbots and virtual assistants. Thanks for watching. In the next video, you'll learn how to distinguish between structured and unstructured data, and you'll also get an overview of 3 different AWS services that you can store text for your NLP application.